Hello, everybody. Good morning, good evening, good afternoon, and thank you for joining yet another Neo4j Live. Today, we have the topic of lessons learned from real-world graph app development with Dave Aitel. Hi, Dave. How's it going?
It's going great. Hopefully you can hear me.
Yes, I can hear you well.
Excellent.
See you also. Good. Cool. I'm looking very much forward to this episode. Should be good. Should be fun and interesting to hear about some of your lessons learned, some about, pitfalls maybe to avoid, best guest cases, tips and tricks and stuff like that. So we talked a little bit about this before last week, and I think it's very exciting what you have in store today. So I'm very much looking forward to that. Before we dive in, I have a little advertisement to make. Notes 2023 is coming up exactly over here. It's happening in October, 26th of October. It's all online, all live. My colleague Michael Hunger tirelessly worked away this week on agenda building. So if you have submitted a call to the call for papers and you're wondering what's going on with that, you should hear back from us next week with confirmation. So we received so many calls, so many submissions, for the call for paper, that it was a hard choice for him to make. But I think he's got through it. Over 90 sessions in the end, I think is what we will have. And yeah, very, very good, very interesting sessions, very interesting topics all around. So I'm looking forward to that event. And we even have a trailer, which I'm going to play now. So 30 seconds of your time for notes. Here we go.
What event brings over 10,000 developers and data scientists together to share how they use connected data with graph technology? Get hands-on at Neo4j's online conference, Nodes 2023. Tracks include intelligent applications, machine learning and AI, and visualization, led by experts from the global graph community. On October 26th, Nodes will be live for 24 hours in time zones across the globe. It's free, so why wait? Register today at neo4j.com/nodes.
Exactly. Register now to save your space. So that's very cool, very interesting. I hope to see you all there. It's going to be a fun day. So you can register already ahead of time. And what's new, and that has just been done, I think, this week is when we completed this, is the Road to Nodes workshop. So I think maybe a couple of you remember, if you have been there, we did a couple of workshops ahead of Nodes, 4 weeks of workshops, every week one workshop. And this week, this year, we're going to do it again. It starts in September, 20th of September. So if you click the link in chat, then you can register for these workshops. Very interesting sessions. Intro, obviously, you get the beginner stuff. But then also we go more in advanced topics like graph data science with generative AI, which is a very hot topic. And Will Lyon will do something about geospatial data and how to work with that. So yeah, that is my little pitch on notes. But now we go to you, Dave. We go to the actual presentation and to the actual topic of today. Before we dive into the topic, I would say let's spend a few minutes of you telling the audience who you are, what you do, maybe, so everybody gets to know you a little bit better. If you would.
Hi, everybody.
Yeah.
I actually have a little section in my presentation about who I am and what I do because I put it into context. But
okay.
If I was going to talk about like where this presentation is, I think one of the great things about Nodes is the beginner, intermediate, advanced selection. Like I've definitely watched talks out of all three of those. And if I had to put this talk into that thing, I'd probably put it in intermediate. Like you're kind of expected to know that Cypher is how you interact with it, right? Like, and kind of some basics in Cypher. But some of the advanced stuff I think really talks about like GDS and graph learning and all that stuff. And I don't go into any of that here. So I'd say this is like an intermediate thing, but it's sort of like what I wish someone had told me as a developer, right? So I guess I'll just start throwing into it. How do
Of
I
course we can.
actually show you the slides?
Here we go. Yes.
It's all good. All right.
Yep.
All right. So I'm gonna just start. All right. My name's Dave Aitel. And I just made a really generic title for this, just building data analytics in Neo4j. And if you have any questions about this or really anything in the world at all, then just, I guess hop in the chat or send me an email or something. I'm sure you can find me.
Hopping in chat is usually a great idea. So while we're live, type in your questions and your remarks, and I can read them out.
Perfect.
Yeah.
And then also, like, if you're watching this recorded 5 years from now, you can still message me. It's fine. I'm on the Discord, the Neo4j Discord. I'm also available via Twitter or email. It's not hard to find me. Okay, so like a lot of this literally, like what I really should have titled this was like feel my graph database learning curve pain, right? So that's kind of like what I wanted to do. And I wanted to like present a little bit about how because I've built a few pretty big data analytics platforms with Neo4j over the past couple years. And this is how I feel like it goes typically for me. And your experience may vary. So again, I'm not like the super most advanced person at anything really. But this is how I do it. First, I just import some data and I shove it willy-nilly into the database really slowly because it's going to be all unoptimized. It's going to be terrible. I try to figure out what the unique keys in my data are because that's a really important step. And the unique keys I want to be referenceable in the outside world, right? Like what's interesting in my data, but also unique about a particular data record. And then I try to just figure out some basic queries and relationships, like what is it I want to do? Because right, a lot of times when you're doing data analytics, you don't already know what questions you want to ask of your data, which I think is what makes these platforms so unique. Like that's the reason I'm using a graph database, which is sort of like, data type agnostic in the first place, right? Then I'm gonna spend a bit of time figuring out my indexes, which is an important part of doing this work. A lot of people, I've actually dealt with like some pretty experienced developers that just didn't use indexes, and I'm like, what are you doing? What is it doing here?
Yeah.
And then
it's an oversight you can make, but you should not.
I know. I'm very confused about that. And then I spend a lot of time optimizing my data import. Data import is an underrated difficulty with any database. And so optimizing your data import pipeline can be really important, especially because the types of data you load in a graph database are often a little more difficult to import than the types of data you'd load in a different database or a different system. And then I build like a big analytical pipeline, right? Because it's not just about loading the data. You also are going to annotate the data, reconnect the data, parse the data. This is where all my large language model work has gone lately. And there's a lot of optimization that goes into that in terms of increasing complexity and speed, which we're going to talk about as we get into it. And then I go back and I'm like, oh, this is annoying to make these long queries. Let me just add edges randomly that connect things that I think are important so that the queries can be faster. And then I really work optimization. I spent maybe 2 months optimizing in the past, year, just straight up. So people underestimate some of these, how this process works. And they're like, okay, I've loaded the data. Let's run an algorithm on it. I'm like, all right, it's going to be a little more complex. So why me, right? Why am I here? What kind of data do I talk about, right? So I find that there's like 3 basic graph database markets. And this is just me making stuff up because of what the people I know that I talk to on Discord, right? So some of them are commercial people and they're like, I need to detect fraud all day long, fraud and trying to make more money by recommending, Beanie Babies to people who bought other kinds of Beanie Babies, right? Like it's like bread and butter corporate work. I find that stuff really boring, so I don't do any of that. Then there's people who are doing like web app development, right? So GraphQL stuff. I don't know how to do any of that, right? Like that's like too much people oriented. I'm not people oriented. And then there's like people who have interesting data, right? So I operate mostly in the US federal market. And that's Like, so when you're doing data analytics, I want to like learn something like science, right? So it doesn't have to be federal, but like if you have a bunch of frogs and they're connected to other frogs and you want to figure out how this data comes together, then graphs are often the right solution to that too. So my personal history, I went to a school in upstate New York. I call it the armpit of New York, Troy. It's a beautiful place. Then I went into the National Security Agency and then out into like consulting. And I now run and participate in a small consulting company, mostly focused on federal work. And the work that I largely did that you're going to see here today is called Regent. It's a DARPA-sponsored program. DARPA is a United States Defense Department research funding agency for people who are not invested in that world. And the program that this is all done under is Social Cyber. I worked closely with another company called Margin Research. And the basic theme of the the larger scientific task that we're like working on is securing open source software. And that means having situational awareness on the code ecosystem and understanding the code ecosystem. It's surprising how little we understand about how open source software is built and maintained. We basically understand nothing. That's where I'm at with that. And because the part of it is because the data is so complicated, right? Like it's like get trees. They're not really trees. They're like, bizarre graphs, email chains, metadata of all types. All this semi-structured data has to get correlated. And if anytime you hear semi-structured data has to get correlated, your brain immediately goes, I need a graph database. At least my brain does. So maybe other people's brains, not so much. But anyway, so that's where this came. This is what I look like if you're like curious in the future what someone wearing a terrible suit looks like working for the National Security Agency. That's me. So yeah, I'm not known for fashion, I guess. It's one of the things. Okay, so importing and connecting data.
Dave, one
Yes.
question I always ask, and I think that's interesting. How did you discover graph? I mean, when I look at the picture, when I listen what you just described, your governmental NSA kind of pathway doesn't, at least to me, and maybe I'm wrong here, but it doesn't sound like cutting edge graph technology right away. You probably worked with other tools first, and then you decided, graph is a cool concept. How did you discover this? How did this come across your path?
Well, the company that bought my first company owned another company called Brainspace, which is it's for legal discovery, and they did a lot of graph work, and I was like, oh, this is interesting, and it's useful for other problems.
Yeah.
And then I started using dgraph, which is another graph database that completely fell apart. But that's where I sort of got more into actually how do I do graph database work. And then when dgraph fell apart, I'm like, I need a real graph. This is ridiculous. So I mean, and I've always been a Python programmer. The Python API was always a big part of my life. And all the code you're going to see today is in Python. So I guess get used to it. And also I think graph problems, you say like graphs are not government stuff, but actually governments have been really heavy into graphs. It's been a big deal for a long time, and some of them have their own graph database implementations that I didn't feel like using. So that's really what it comes down to.
It's a big topic. It is very 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 popular, and it's absolutely. I didn't mean to say government is not graph is not interesting, or government is not for graphs, but I didn't think like the first technology would probably come to mind. At least, I mean, maybe I'm German, and I think by looking at the German government, they wouldn't think, let's do a graph database. They would probably think, let's do something else first, maybe.
There might be some cultural differences there. I will say, like, a lot of times, especially people who are in the commercial world, underestimate the fact that the government does everything. And there's just random scientists in the corners who are like experts at random esoteric subjects just because they've done it for 20 years, right? So maybe I will be an old wizard someday. I just wanted to put the first thing I wanted to do is put my schema up, because the very first thing I try to explain to people when they start, like especially new developers on my team, is like it's going to look like a ball of twine when you're done, right? Like that's kind of just, that's good. That's not a bad thing. You don't necessarily need a very simple structure, because if you did, that would mean your data was simple, and we're not solving easy problems. So that's the first thing I do. So, okay, so I have 6 scenarios. If I go back a little bit, I have 6 scenarios for importing data that I collected. That's sort of like walking up the path, walking up the mountain. So everyone gets to walk up the mountain with me. The very first thing is like you have a tiny amount of data that you want to import, and it's pre-processed in a comma-separated value file, right? Like, so like when you look at demos online, 99.9% of the time, this is what they're doing, right? So this is like an example. Everyone imports the Enron email corpus, right? They're like, we've got 150 users, 500,000 messages, you know, a total of like, I don't know, 183 edges, right? They're like, I got this a little bit, and it's nicely split up, and we load it into our graph database, and we do like some algorithms on it. We're like, look, this stuff works. It's amazing. And there's just not a lot of public data sets that are of real size, right? So this is one that everyone used for demos forever. Every legal discovery company, everybody else. And this is how you do it, right? So it's sort of like load a comma separated value file, you know, into these rows, and then I match them and I parse them, and I'm like, you know, then I merge the contacts and I make these little edges, right? So that's awesome. But like, this is my tiny temporary development database, has 75 million relationships. Like, that's the kind of scale that we're talking when you're just demoing technology in a real world situation, right? So I've got 9 million nodes and I got 75 million edges. That's normal. I just want people to understand what scale is like at the bottom end of this kind of technology before it starts getting interesting, right? So you're trying to develop code that can handle orders of magnitude more, right? So like, you know, 1 billion edges is not weird. So, so that's sort of like, I don't like the demos because I think they set people up to think things are different than they are necessarily. I want people to demo on real sizes of data. That's where it actually starts getting interesting.
Yeah, you might get the wrong impression, right? I mean, the demos we provide are very condensed, very small scale, so you kind of understand what's going on. So even if you don't understand the data set, because it's not your data set, so obviously you have no idea of what's the concept. So you have to learn the data set, but then you also have to learn the technology. So it's very complicated. So if the data set is small, then you understand and say, oh, okay, I get this. This is what's going on here. But I agree with you. It kind of sends the wrong message. Okay, yeah, data set is a couple of hundred nodes and a couple of hundred edges, so it's very, very small. It's like, okay, but this is the play tool. But you're right, it isn't. It's just for getting the concept.
And that's I think that's just an element of like, how do I demo anything, right? It's like, I'm not going to have a lot of like they're not going to, like, I can't have a server that 600 people connect to that has like 1 billion nodes in it, right? Like. But that's what you kind of start wanting to have at a certain point to demonstrate some of these technologies, like some of the machine learning stuff in particular. So, and this is something where I start like with our junior developers. I'm like, you know, here's your playground, and your queries have to work in the playground at like real scale before you move on. So, I guess my second scenario. Sometimes you can just fit your data in your laptop's RAM. Right. So that's where you start just iterating, right? Like, because you're trying to build processes in your heads. And so this is like an example. This is real world code that adds communities to the database, right? So once I have a bunch of code blocks, I want to group those code blocks into communities. And the way I do that is finding relationships between the files in that Git repository. So here you can see when I get all the communities, I'm literally just asking the database to just give me all the communities in a repository and just load them into my RAM. And then I want to find the top files. So for each community, I ask it, you know, give me the top 3 most important files in that community, right? So it does that. And then here I'm going to add that community I'm going to add the top files to the community with these properties. So I'm passing the properties in as a little dictionary. Here, I'm doing another query to get the files out of a community. And then here I'm linking the files to the community, right? So this is just an effort to say what files are in a community and what are the most important ones. And that's it. So you can say I make 4 queries. And then my total transaction cost is obviously, like if you studied like order n in computer science class, I have order n times transaction cost times 4, right? So this is plus the memory cost of loading all the communities, which may be big, may be small, depends on your lifestyle, right? So that's how you start. It's because what you're doing is you're building the algorithms. This is not the final version. And I think a lot of people stop here and they're like, this is the final version. It's fine. And I'm like, that's not fine. That's not how we're going to live our lives. So scenario 3, you get actual data and it doesn't fit in your RAM and you don't have all day. And by RAM, in this point, I'm starting to also think about RAM on the server, right? So when you have real data, you invariably going to start wrapping almost all your calls in this, all your queries in this, right? So everything gets wrapped up. So I think what I learned was like I had one function in my program that just deleted my database so I could restart from fresh with my import. And once your database gets to a certain size, you can't just select all the nodes and delete them. You have to do them 1,000 at a time. And that's where I realized that, like, okay, this is a pattern I need to start using again and again. And you'll see it here, for example, like when my second version, when I attach the files to the communities, I get the repo. I say, if you have a community, then I call with the community and I say, all right, now I need to match. I do that match with the files and I say, give me all the files and connect all the files to the communities, basically. And I have to do that 1,000 at a time. So 1,000 communities at a time. Otherwise, the memory was not accessible by the server. And the other thing I always point out at my junior developers is this coalesce call, which is an extremely important call, because if one random file does not have a community for some reason, you don't want the query to die. You want it to just be a null here. So this is an important thing to learn about how to build your queries. Is like, because the cool thing about the database is some files may not have a variable, right? So you're like, it's a untyped node. Anyway, so this is the next pattern. The next pattern is, okay, I'm going to have to wrap stuff in transactions to control memory use, because otherwise it's not going to work. That's where we're starting to do that. Okay, so now I have something complex I want to do, but I want to use all my cores because otherwise it takes forever. And I think what people don't realize is that by default, one query is one core, right? So they're like, I have 5 cores, I have 30 cores, I have 100 cores. If I make a complicated query, they're like, well, I expect the query planner to split it up among the cores and use all my processors if it can. It does not do that, right? So each query, one core. And that's where you start really seeing, I'm going to just this particular code here, it creates a directed graph of file nodes based on their connectivity to each other through git commits. So if 2 files, like if readme and maintainers.md are always committed together in the same git commit, then they're tightly connected. That's the basic theory of this code. And you'll see as we go through that, like, as you get more into controlling memory versus CPU, you're going to rely on apoc.periodic.iterate. It's just going to be a core feature of your life, which takes in 2 queries. First query is sort of like generate a bunch of keys or a bunch of nodes. Second query is going to like operate on those nodes, and you can do this in a parallel fashion. So this is the way I had 22 cores. I'm using all the cores. I'm doing it in a batch size of a certain amount to control memory use if I can. So processing batches of data here, I call this algorithm Descartesian, because it's not Jacardian, which is a way of finding connections between things. It's a directed graph, and Jacardian does undirected work. But also my name's Dave, so those are the 2 reasons I changed this algorithm. It's a slightly different algorithm that does a very similar thing, but better for my purpose. So this is like a scenario that you're going to start to do. You're going to start to like want to use all your cores because you have enough data and it's sort of a bursty process to do analytics. Sometimes you just want to use all the cores. With like a GraphQL style kind of app, or an app where it's sort of like you've got a lot of users connecting to it, they're each doing one thing. You could see how like having just everything use one core makes more sense in that sense. But for a lot of the analytics, you want to use all the cores. So that's scenario 4. Okay, scenario 5, like it made me cry. So this is like, people are like, well, how complex can the queries get? And I'm like, well, they can get complicated, right? This is one query. I had to split it up on 2 pages because
yeah, okay, yeah, that's a long one.
right, like, so and this is one of the core algorithms in the product, in a sense, right? So it goes through and it finds maintainers of a group of files, right? So the key theory here is, let's say I have Linux, the Git repo, and it's 1.5 million commits, right? Like, or something humongous. It's just a lot of code. Each of 45,000 files is maintained by some group of people, but who? Right? Like, I want to know who the top committer to that group. How do I even split up the files is the first step. And then once I split up the files, how do I determine who's maintaining them? So that's like, these are annoying problems to solve, right? But this is how you solve them. But I want the graph database to solve it, because you want to put as much of this logic into the database as possible, because if you're doing it via like transactions, it's going to be unbearably slow at that scale. So how do you do this? You're going to use APOC periodic iterate. It's going to be an obscenely complicated version of it. What we're doing here is we're getting communities, and we're passing communities into this humongous function that you can see just keeps going and going and just does crazy stuff to account for various things not existing, and maybe there's not 3 files in the community as well. So this one function took like 2 weeks to get final. Like, went through a lot of iterations to generate the right data. Yeah. And then in the end, you're spending a lot of time trying to figure out, because you don't know the shape of your data in the future. This is something that I try to explain to people when they try to optimize for various algorithms. They're like, well, I'm using Louvain instead of like label passing. And I'm like, why are you optimizing for the current shape of your graph? You have no idea what future graph shape looks like when you actually import more data. And so you have to be extremely conservative sometimes with how much memory you're going to use. And the problem is I really liked Parallel on this thing, because Parallel made this go really fast. But some of the communities, it exploded my memory use and then would, die. And so in that case, Parallel I had to turn Parallel off, which made it a lot slower, but it guaranteed the finish. So this is like, you're going to start to play with batch size. These things, this is where like performance optimization becomes a thing. Like, you're going to spend a week performance optimizing a complicated query and making sure it finishes on all of your data potential. So anyway, lots of fun trade-offs there. Lots of fun. And then, so like final scenario for this is where I always end up when I do import, which is I load the data in batches. Understanding how to create those batches can be complicated, because the basic scenario with import is, a lot of times you're like, I want to import this data, and I want to connect. Let's say I want to import a repository, and I want to connect it to a user only if that user already exists in my database. Right? There's like I want to make an edge, but only if the thing actually exists. There's a lot of like, how do I connect these things up properly, and how do I handle the metadata? So what you always end up doing is loading the data in batches. If you load it one at a time, it takes forever. You end up loading it 1,000 at a time to increase speed. It almost always looks like this at the beginning, right? So it almost always has an unwind of a list of rows where the row is actually a dictionary, right? So this is In this case, I have a dictionary. The repo has a database key, and I find the repo, and then I just set all the properties from that dictionary. So most people do not know that you can just set all the properties out of a dictionary into an object. And then I use that repo and I match it, or I match, I use ID here. There's, you know, it could be used element ID. It's the same basic thing. And then I connect it up to the parent, which is, you know, the parent node ID is in there somewhere as well. So it's here. So this is every import you do eventually becomes unwind and then set, right? From all these things. You're going to unwind a list of dictionaries. And then how you order it is really important. You can see here some more. This is realistically how it works. On create, I want to set this stuff. I wrap everything in this transactions thing because I have to do that to make sure it works properly. This allows me to pass essentially arbitrary size lists into this function and have them handled without blowing out my memory. So these are the things that like I wish I'd known when I started. Is this little pattern of code is repeated in many projects. You'll notice here I actually load all 3 of my things all at once because they've all been, and I also unique them, and I do a, you know, this is like what a real importer ends up looking like for me. A little trick that I don't think most people know is you can actually plus equal off a dictionary into a node. And these are the little tricks where I'm like, hey, for like, you can see me complaining about memory use here as I like figure out what's going on in my life. So this is just bits. This is like things that I didn't know that made my life a lot easier, right? So what does a real importer look like on the ground? So imported data. Okay, so now I've imported my data. And that's like, that was a big problem. So graph projections, right? Like I was trying to explain, I had a new developer come on a couple weeks ago and I'm explaining graph projections. And I'm like, every graph can also be transformed one-to-one to a matrix. And it's a lot easier to operate on as a matrix sometimes. And then you can transform it back into a graph. And I'm like, so just like that's the basic theory is I want to store a matrix of numerical values in memory. And I want to like operate on it in memory. And then I want to save out the data back into my graph and have it persist onto the disk. That's basically what I want to do. So when I make queries, it's in graph. And when I do operate like complicated operations, it's in the memory. So this is like, if you talk on the Discord and I'm like, I'm having problems with operating my graph, people are like, just use native projection. It's almost always the wrong answer. And it confuses me why people do this, right? So the pros is it's super fast. The cons is it's your whole graph, right? So your whole graph goes into the memory and then you operate on it. I almost never want to operate on my whole graph. I can't think of a single time I've wanted to do that. So like, but this is how you would do it, right? Like I originally did have some code that did it just to page rank the entire graph for fun. So you can pick like what nodes you want. You can pick what edges you want. You can say what orientation you want those edges to be in. Sometimes you want them reversed. Sometimes you want them undirected. That's fantastic, right? You can estimate how much memory it's going to take to make sure you have the memory. And then you can just go do it. Honestly, the estimation, I don't use it anymore. And the reason I don't use it is because in a very complicated analytical process, I can't say I'm only going to be doing one graph operation at a time. So it's pointless for me to estimate how much RAM it takes unless it's like, because I could be doing 8 of these at a time. So if it takes more than an eighth, right? Like, so it becomes like not useful for me. So I just blindly do it. If it fails, it fails. You know what I'm saying? Anyway, this is the way I used to do things. And it was like, it's not recommended by anybody. Everyone's like, oh, please don't do that. But like, this is the only way it worked for a long time. So the subset of your graph is what you want. And then it looks like this. Remember that like unlicensed GDS, you get a read concurrency of 4, which means you're reading with 4 threads out of your database into memory. And then you can turn off. One thing I did is I turned off relationship validation. So if there's like a relationship to a node that's not in my projection, I just didn't want it to error out. It's fine. I tried to improve this a lot and I could not figure it out. But basically there's if you're doing projections here in this with this API, which still works and it's still a good way to do things, you can match first the nodes, and then you match the relationships you want, and then you pass, and it sort of like makes your graph for you. And then this thing down here, this node similarity, actually replaced my Cartesian thing and made it 100 times faster. So I ended up saying, you know what, Cartesian's good enough. Let's just go with that. And the trick for doing this is that I had to reverse the direction of my edges, which I did not know. Right. So this is a lot of the algorithms are really complicated to understand how they work. And so in this case, you can see that I actually return the ID of the file, which is the destination of this edge. This edge actually goes from git commit to file. And I have to reverse that. I make it file to git commit, or actually, yes. So I make it file to git commit somewhere. And then so that reversal is what makes node telemetry work. So I tried for like a week to try to get this API to work, failed, asked online. One of the developers was like, hey, this is a segment of my book coming out that you can read that actually tells you how to do it. I'm like, okay, cool. So that's like, once you've sometimes you'll have something completely working in Cypher, like that you've optimized for literally a month. And you'll be like, oh, now a GDS function came out that does the same thing or close to the same thing. I'm just going to move over to that and it's going to be better. Right? Like that's the reality. So I felt sad throwing out my code, but but this is faster and better. So, and it works roughly. It's not like as good in terms of results, but it's good enough. And the speed performance benefit was humongous. So, and I wanted to you can, I don't talk about it here, but like optimizing how you use graph algorithms is like a whole separate talk that you can do.
Oh yeah.
And I could do, and I don't want to. So. Okay, here's the modern graph projection, right? So this is going to be the only documentation that anyone has ever seen for how you actually do this, because it took us a while. It took us a whole day to figure this out, actually. And again, it's like underneath 5, I think it started in 5.5, or I can't remember what actually it started, but it was an alpha. So now it's not alpha. So now you can actually use it. This is like what I wanted to do, because like some of the examples, they're like do this union of, so you basically have to define source, target, and relationship, and then union it all together. Because I'm pulling up pieces of my graph. I want a full subsection of my graph in the projection. So I have pieces of it, and I'm like, okay, I want that query, I want this query, I want this query, and this query, and each part of them generates a source and a target and a relationship. And I want to union them all up and then make the projection. And Neo4j was like, you cannot do this. Like, this does not work. This, like, when you do this first return, we're done. Like, knock it off. Right? So, but it was like, this is like conceptually what I wanted to do. So I'm like, okay, but there's got to be a way. There's got to be a way. And so for tiny data, this is how you do it. Right? So this is the exact same matches. And then I collect everything as lists, and then I add those lists together with these two with statements. So you can see here I have with these things, and then I add them together as like lists add to lists. You have to do it in 2 lines. You can't do it in 1 line like you want to, but that's life. And then at the very end, I have this huge set of sources, targets, and relationships. And I'm like, winning. I've got it. And then I use APOC. You almost always end up using APOC. So, like, why is APOC not installed by default? I don't know. Anyway, so almost always use it. And then this toSet is going to remove duplicates, which is important because I want to, like, that's a very quick thing to do. So I'm going to just remove the duplicates so I get the real sizes. Now I can just unwind them. So I just unwind sources, I unwind targets, I unwind relationships, and now I put them right in this little thing. I'm a bobber. And then off we go to the races. And this totally works. This totally works. One thing I want to point out is I want undirected edges. And a lot of the graph algorithms, you want undirected edges. So, so that's why I did that. I don't have any properties on my edges, but that's a separate discussion. If you're going to do properties of any kind on these objects, then you need to have that coalesce function before, so that you make sure you do. Otherwise, it throws or used to throw a Java null pointer to reference, which is annoying. They might have fixed that in the latest version, actually, between 9 and 10. But anyway, so that's a separate. This is all documentation you don't have yet, but now you do. Okay, so important to remember. Unwind is a for loop, right? So this is actually 3 nested for loops. So for small data, you're like, this is cool. It works perfectly well because for loops, whatever, who cares? And then you're like, wait a minute, for actual reasonable sizes of data, these unwinds never return because it's just like an exponential for loop. And I'm like, oh, there must be a better way. And so between me and GPT-4, I'm like, we're going to find a way. Okay, so let me scroll in a little bit and show you the magic, which is this line here. Oh no, it's this line right here. I realized I don't care about the nodes. I don't need to collect all these nodes going through, make lists of nodes. No one cares. A relationship has a front and a back. So by definition, I can say, give me unwind the relationships and then use the nodes at the front and back of the relationship. And that's all you need. So, so because of that, you instead of 3 unwinds, you only have 1 unwind. It's the unwind is like order of the size of your relationships, which you've already you've made unique. This is the working version. So if you're confused about how to do it, this is how you do graph projections forever for the future. Is you just worry about the relationships, use this line of code, you're good to go. That's how you do it. If you want properties on it, use coalesce to make sure that it doesn't have an error. Simple. Okay, so that is the next step. So being able to obviously the whole point of using the graph database is to use GDS, right? So like that means you have to do projections. If you're going to do projections, you almost always want to project a portion of your database, not the whole thing. And then this is how you're going to do it because it's cool and it works really well. Anyway, that's the new way. So learn from my pain, I guess. All right. I'm going to start going over a few things in terms of like things I did not know about graph databases. I don't have like a formal graph database education of any kind. I probably should have read a book, but I didn't read a book. And your developers aren't going to read a book either. Let's be honest. No. You know what I'm saying? Like, I didn't read a book. Yeah. My developers aren't going to I'm like, when they start the project, I'm like, here's a 200-page book on how graph theory works. They're like, great for you. It's like not a thing, right? They're like, so like even the idea of like a Cartesian product is like, they don't know that, right? Like that's not a thing they know. So I'm like, please don't put commas in your query, even though you can. It's like what I say. But actually, this is a really valuable learning lesson that I learned, which is that not only are Cartesian products bad, but combinatorial explosions on real sizes of data are fatal as well, right? So my developer, who like was pretty experienced, was like, here's a query that I have that just never returns. And he's like, it's not even that complicated. This is exactly, it's like the whole point of Cypher is that you can describe it in English in a sense. And it makes a lot of sense, right? He's like, I have a repo with this particular key, which it's uniquely identified. That's super fast to get. All I want to do is get these targets that are these files. I want to get all the files that are included in it, and then tell me all the users that commit to that repo, and then tell me all the git commits that they do. And I want to make sure those git commits modify this target, right? So he's like, why doesn't this ever return? He's like, I don't understand. Every piece of it is fast, but this thing doesn't return. And I'm like, oh, let me ask GPT-4, which is like my go-to, right? Because I'm like, I don't understand it. I don't know. But let me ask GPT-4. GPT-4 is like, here's a better query for you. And I'm like, okay, so you match the users and then use those users and the git commits. And then you pass that into this other thing that matches the files. And I'm like, this is the same freaking query. Why is it any faster? Right? That's a really hard question to answer, it turns out. I don't know. Like I'm like the senior developer, and I'm like, I don't know why it's faster at all. I have no idea. So I'm like, how is this a Cartesian? Because I asked GPT-4, it's like, oh, you have a Cartesian product. And I'm like, really? It doesn't look like a Cartesian product. And they're like, actually, it's not a Cartesian product. It's not one. It is the fact that these relationships form this complicated connected pattern. So it's actually returning back this huge set of paths So the total number of results is not the product. It's just a humongous multiplication of the product, what they call a combinatorial explosion. So if you have a lot of these relationships, then like they multiply together, right? So each user has a lot of files, each git commit has a lot of a file and users. It's all like, okay, so it's not a Cartesian product, but the query has a large number of paths that match the pattern. So they split up the query. And I think like understanding this simple concept made a lot of my queries 10 times faster, like, or 100 times faster. And this was something like, I'm like, if you can do it in 2 match statements instead of 1 match statement, do it in 2. It's just going to be better.
Yeah.
So I don't know, maybe there's like a beginner's course on Neo4j I should have taken that would have told me this, but I had to learn it the hard way. So it's in this presentation.
I don't remember if it is in the beginners, because it's like, yes, make it as simple as possible. Space it out a little bit more if you can. Don't put everything in one match clause. That is definitely an advice we give. But
But why?
Yeah.
And this is why. It's like it's the difference between query work and query not work. And I think that's an insane, like this was like I mean, he was probably spinning on this for a week trying to figure it out. You know what I'm saying? Like anyway, so lesson learned.
Yeah, it can be frustrating because you don't know. I mean, this is, like you said, I mean, should work, makes sense. Everything, single individual point of it is quick and fast and returns something. So why isn't it coming
correct?
Back?
And I was like, I don't know. So like, I don't know. So that's like, and here's another thing. Here's another lesson I learned.
Maybe what, I don't know if he did that, but maybe what could have. Okay, yeah, I see. Okay, well, I shut up.
No. Say it.
I wanted to say, try the query planner and have a look at it and see if that.
It didn't help. I got to be honest. It didn't help because the pieces were actually really fast.
Yeah.
Or something. I don't know.
Yeah.
But I will talk about the query planner now, because the query planner is like, I'll call it like the core feature for figuring out how to make your queries. It's really important. Really good, but very misleading. So I want to say one like very lesson learned that I had one day, and no one else has to learn my lesson because they watched this presentation. So edge names are queried before label names. In my head, the query planner would like look and be like, it would be like, well, there's only like 10 user nodes in the whole database. Let's filter on user node first. How, like that was what like the query planner would do in my head. But in practice, it does not do that, right? So a lot of times the row estimation is a lie. And understanding how it works, like understanding the boxes, is a really big deal when it comes to figuring out query speed issues. So this was another thing that was making one of my queries like really bad. So here you can see like I match the repo to the community, and I don't use an edge. And you can see here it's 1600 milliseconds. And this is just a really small database, so it's not that big a deal. But nonetheless, I'm like, okay, that's the value. And if we look at the query planner or the explain, we get like, okay, it does node by label scan, which makes sense, getting all the repos. And then it's expanding all the edges that go to anything. And then it's checking to see that those edges or those new nodes are in a community, or a community node. And then it's counting out the results. So you can see it's sort of estimating 5 million rows or whatever. That's a small database. Okay, so that's an important, like I was like, why is this query slow? And the answer is that if you have the edge, it's like you can see the difference in speed. It's huge, right? So sometimes you'll have like, let's say an owner of one. So one node goes to a parent and only has one parent, but that node also has 3 million other edges to other nodes. So it's important to note that if you had put the edge name, it'd be 3 million times faster, because it only has to return that one node instead of going and returning them all and then filtering by the labels. And you can see here that is exactly what happens here. This actually is wrong, right? It doesn't know that there's only 5 communities. So it thinks that there's 400,000 still returned. And so that was important to me to understand that, like, if you ever have a query that does not have a relationship edge type, you're probably making a huge mistake as your data sizes get bigger. or as your graph shape changes. So that was something that I had to explain to everybody. And if you look at like pro level code, they always have the edge name. They never just connect. And I thought, oh, that's very interesting. So, but it's like a lesson that I had to learn the hard way, and now no one else does. I guess the second thing I had to learn is like, don't necessarily rely on the size of these little things. Like sometimes they're wrong, and that's okay. Like read what it's doing instead.
Yeah.
So that was a valuable lesson learned for me. Indexes. I learned some lessons with indexes. The first thing I learned is have indexes. Like I had a developer for like, I think he was working for a month with a database that had no indexes and everything was taking a half second. And I was like, what are you doing? Like, it's ridiculous. So basically for almost all your search queries, you want to have an index that you search with, but not all of them, because there's a weird limit to how big your data can be in any indexable field. So, and that weird limit is like around 32 kilobytes. So if I have like, for a while, I was storing like email addresses or emails, not email addresses, but full on emails in a field. And some of them were pretty big. Yeah. And I tried to index it because I wanted to search on that stuff. And it turns out that works really well for smaller emails. But once you have an email that's reasonably big, it just errors out. And you can't do that. So that was something that I did not realize. And I actually filed a bug report for this, because if you have a bunch of emails in your database and then you try to create an index, it gives you a weird error. And you're like, what is this error? I don't understand it. And the error actually is you have one random like field that's too big for the indexer to index, and it'll just, it won't tell you too big, kill it. So you'll have to go through and find that yourself. Oh, and it's also a random amount. So I put 30,000 because it's around 32 kilo. I don't know what, there must be some metadata it's storing as well. I don't know what it is, but that's what it is. Anyway. So this is what it looks like when you the first thing I do with a new database is build this, is like load my schema. And this is what a schema looks like, right? So a bunch of texts, some range, every node has a constraint on a database key that I'm going to find with it. So like every single node type has, and I just think like that's something most people, I don't think I've ever read anything where they're like, this is what you do. Your schema exists as a thing. You load your schema first. And then, so like, anyway, that's an important part of your life. And then choosing what that unique database key is can be a big deal, because you actually, like, especially if you're referencing external data, you're not going to use like a UUID. Your database key that you're going to find something on is whatever's unique about your node, right? So in this case, like, every topic has a name and the names are unique, right? Like Debians have a name and the name is unique. Pips have a name. GitHub users have an ID, and that's it's guaranteed unique by GitHub. It does not change. Yeah. So, so when I go to GitHub and I make an API query, I can then correlate that with my database. So that's like, this is some very basic stuff, but I think like people don't understand, like some of these can be difficult to pick out. Some of them you can be like, well, I don't know if it's truly unique and truly immutable. Does it change over time? Not in my database, but in the outside world, because I'm trying to connect to real data in the outside world. True. Right. So, so that, like, I think, and, sometimes you'll spend like, a week figuring this stuff out, and that's just normal. Okay. So now I just have a conclusion, very simple, but I do like to touch upon, like, this is the process that we went through in my talk, right? Is like optimizing queries, adding edges. We didn't talk about adding edges, but some other talk perhaps, iterating and doing all these things. That's the process. So all that's left is the conclusion, which is the value of using the graph algorithms is huge. It's huge. So for this particular project, Linux, if you've dealt with the Linux kernel, it has a maintainers file. And that maintainers file tells you who's maintaining a particular region of code. So they've split up the code into little regions, and they're like, here's who's maintaining it for any large project, right?
Yep. Being
able to run graph algorithms tells me, first of all, what are the real regions of code? Not the ones that are just in this random file that no one maintains, the maintainers file. But what are the real regions of code? And then I use simple graph algorithms to do that, very quickly for huge amounts of data. And then, who's actually maintaining it is another graph like that's that big query, right? So that's another graph problem that I'm going to solve. So like the value can be immense to organizing the data properly, to going through this process. Now that I understand, now that everybody who's watched this video understands what that process looks like, you're going to be able to import really large sets of data and then operate them on a way and get insights in a way that, like, I think otherwise would be basically impossible. But these are the things that I had to learn to get that value, right? Like the learning curve is still pretty hard. So, so you don't have to spend a year doing it. You just have to like watch this talk for an hour, and now you know everything you need to know to get that value. So that's the talk. That's all I had.
Cool. Amazing. Thank you very much, Dave. That was great. I had a couple of questions came in, but I didn't want to interrupt your flow. So I'd like to do them now if you have a bit more time.
Let's do them. Yeah, let's do them.
So let's start from the beginning, where we went on and explained about the imports part of it. Also, maybe more of a comment from tomorrow on YouTube. Graphs are nice. Yes, graphs are nice, and anytime data is related and rows are not necessarily complete. So I think that's another interesting point, right? For advantage of the graphs is like, yeah, I mean, you can have gaps in your data, you can have missing information, but in a graph it still kind of works out.
That's a good point.
Then a question from Ken. At that, I think that was also back when we talked about import. At that scale, did your graph start off with a smaller set of data and it was built up to what it is now? Or if it was built up, please take the process of adding an additional data to your graph. So I think you mentioned you had a big millions of nodes graph right from the get-go. Was this how you did it, or did you actually build it up that way? Or was this basically the minimum number and then you iterated over that from there?
I mean, I start literally, it's sort of like I started, I mean, the DARPA project started, the goal was to import the Linux kernel's Git repository, right? So the initial importer, even though it was slow, was like I just ran it. It's in a cloud, right? So I just run it. And if it takes a week to import 1 million nodes, that's fine. But I'd rather like, you know, like sometimes you're like, this is taking too long. I need to like, and you iterate on your import process to make it faster. Some people build these huge like Mongo and like Redis pipelines where they're sort of like pre-processing the data and shoving it into the graph. And I don't do any of that. It's straight up like put it in Python, iterate through the data, and shove it in the database as fast as you can. So, I mean, your mileage may vary, but yeah, like the database that I think I've had processes running on it for like almost a month now. So reliability, how do you keep your import process continuing? How do you reset and restart? Because you're going to eventually like be like, oh no, something's broken. All that stuff is like a separate, discussion in terms of like, how do you do that properly? Like making sure you have your date times in your data, like a lot cleaning up the data. The previous question was really good. The data is going to be dirty. It's real world data is super dirty. So how do you clean it up and put it in the database properly is a really big deal.
Cool. Dimitar had another question. What's your opinion on the use of in-memory graph databases?
NetworkX is good, right? Like NetworkX is great. Like I don't have a ton of experience with some of the other ones. But like, I guess my feeling is like a graph database, people think is about querying, and I think it's querying is important, but I think it's a lot about the algorithms. Like without community detection and some of the other algorithms, and I use a lot of the algorithms, to be honest. I use node embeddings, I use a bunch of stuff. I do a lot of annotation with lists of vectors. So I have actually built like huge similarity, like semantic similarity searches, in this stuff. So I would say like if I was going to use an in-memory database, it would probably just be NetworkX. Like that's the reality, and I would just invest in a terabyte of RAM.
Eshwa wanted to know if you share your slide deck with the audience, if you can make that public somewhere.
It's on Prezi. It's on Prezi, and I can I'll get it to you.
Okay, perfect. And then I add it to the video description. Perfect.
Yeah.
Cool. Comment to in-memory, from tomorrow. In-memory is good for speed, and modern physical servers have about 4 to 12 terabyte for not too much money, I guess. So yeah, like what you just said. Yeah,
it's certainly possible. But I would say that like I really value persistence as well. Like this data, like
yes.
you know, like,
that's what you don't get.
It's not a bad thing to have persistence, and at a certain level, scale, right? Like this is like I often find, okay, so the government way, this is like a weird thing between corporate and government, is that corporations often scale out before they scale up. Whereas when you go into like, if you're in like a studio in Fairfax, like that's handling drone data or something random, they will, the workstation they will have handling that data is going to be like the biggest thing you can buy from Dell before they scale out. And that's always just one of those things like, yeah, I mean, actually, it's a very valuable process to understand how you scale just to a terabyte of RAM first. There's nothing wrong with that.
No, absolutely. Yeah, and like I said, the persistence, the way, I mean, you can do both ways, right? With Neo4j, you have the in-memory option. You can always do a projection, but you also have your stuff at your
and I also back up my data on a regular basis so I can reload it somewhere else. There's a bunch of stuff that happens, like I like having it on disk. But it's the reality is like querying is important too. So how do you build and how do you iterate on your queries? It can be an important part of your productivity. You know, a lot of what sells Neo4j is the productivity of the analyst. It's not just about like how fast is a query necessarily. I don't know if that makes any sense.
That makes sense. A couple of thumbs ups for your presentation from Warren as well. So thank you very much that you like that. Isaac wants to know, does there come a point where further optimization becomes too expensive to continue, or maybe getting that additional performance isn't worth it?
Sometimes you go in a performance circle. I don't know if anyone else has done this, but like I iterate like on a query, making it like changing it to try to get more performance, and you end up right back where you began. And it just turns out that's as fast as it's going to get. And so the next stage of scale often is like the rest of your pipeline. So you're like, this query is as fast as it's going to get. How do I parallelize? So I'm doing like 6 different repos at the same time, not trying to speed up one query on one repo for me. Right. So that's another aspect of performance management where you're like, I want to have every CPU on my graph database server running, and I want to be using 100% of the RAM at all times to get value, right? Like that's where I'm that's the goal. But you're never going to get there, and you don't, it may not be a realistic goal. And honestly, he's not wrong in that sometimes optimization, like having a simple, understandable query can be much more valuable than having a optimized, complicated query. So, so that's going to be, that's up to y'all. It's up to y'all. Not everyone wants that puzzle either. Like it gets complicated, and you're like, hey, I'm not down. GPT-4 is not down, and I'm not down with some of this stuff.
On the indexing, Sindesi put a comment in. Likely the 32 kilobyte are in raw bytes and lower due to the UTF-8 format.
Yeah, I thought about that, and I was like, you know what? That's just annoying. Because how am I supposed to predict that? You know what I'm saying? Like, that's a possibility. I should be turning strings in UTF-8 and splitting them. You know what? I kind of assumed that's what Python. Oh, it's in bytes. Oh, I don't want to convert everything back for all the time. That's so annoying. But you know what? He's probably totally right.
Warren, another question. When dealing with important large CSVs into Neo4j, or in general large datasets into Neo4j, is there like a proposed criteria one can use to test for data correctness?
I just do it in Python. That's how I do it. You know what I'm saying? Like, and I feel like you're going to have to, because your data is not going to be clean. If your data is clean, then you are a magical wizard from Oz, and good for you. You're like, I've never had a data set that was actually clean. So
it rarely is.
It's just never happened to me. Maybe it does happen.
More thumbs up to your great presentation from Christina, from Eshwa, from Sindesi, from Darion. And I think I have one last question from Darion indeed. Is it better to make the constraints to import the data when this finishes to create the indexes in the DB, or is it better to create them both at the beginning, basically? Or is there a,
well, it's part of the process, right? Like at the beginning, you don't know what your constraints need to be, right? Like, so you kind of, because there's a data exploratory like process at first. And so in general, though, you kind of load the data, understand what your data looks like, delete your whole graph, and then put your schema in, and then start importing again. That's the way to do it. I do have some code where it's sort of like, uh-oh, I screwed up. I better delete duplicates out of my graph because my constraint won't load. So you're going to end up doing that too, but that's obviously not your preferred choice. So every node should have a constraint. There's actually, in the paid enterprise version, there's one where it's like, this is the node key, but I don't use that because I don't necessarily know that my customers are going to have the enterprise version instead of the community version, right? So, which probably has slight optimizations on it, but actually constraints work really well. So I don't know what more I could ask for, right? So, but yeah, it's just one of those rules. You're going to go through, and if you don't see a big list of constraints in your graph like initialization process, then something went wrong, and your developer needs a little education. They need to watch my video.
Absolutely, they need to watch this. Yeah, I think it's easy to forget that. That's an important point, right? We say, and it's right, that Neo4j is technically schema free and you can do whatever you want with it. But once you go in production use cases, please, yes, set up a schema, set up an indexing, set up all these gates for your data set, because otherwise you're going to have queries that run forever. You're going to have issues left and right, and it's very important. The flexibility still is there, right? I mean, you still have, even if you have a constraint on a value, on a node, on a label, you still can be flexible. It's still not like a relation database where you have set everything is like in concrete and you no way to move around anymore. But it helps a lot.
Yeah, it's definitely the way of building analytical applications using Neo4j or any graph database is better, right? Like, it's just a better way of doing exploratory analytics where you don't know the answers, you don't know the questions, right? Like, that's just the way it is. So for that set of problems, I would say, and that's why I got into this in the first place. I didn't know the questions I wanted to answer. Like, and that's the reality. And I want to find out by looking at the data. So next up, I have a whole thing on Bloom. I should do a talk on Bloom too.
Yeah, absolutely. That would be great. I think we're over time already by a couple of minutes. Thank you very much for sticking around. Thank you for your questions. Thank you for the great presentation. I can only echo what the audience said, Dave. It was really, really insightful, really great learnings, really interesting points. Where I put a couple of links into the video description already now to some of the things you made a shout out to, like the indexing, like the constraints, like the periodic commit, APOC in general, coalesce, and so forth. But for other stuff, I will add your the Prezi link as well, so people can look at that afterwards. The video is up. Share it with everybody who's working with Neo4j who needs to know this. Obviously, this is definitely good to learn and good to hear. And in terms of next topics, next week on Tuesday, I'm talking to and I forgot his name. Sorry, blanking here. Talking to Dulkifli Bukra from the University of Algiers about metadata management of NoSQL data sources with Neo4j. So that's happening on Tuesday. And yeah, with that, I wish you all a great rest of your week, rest of your day. Thank you very much, Dave, again. If you want to talk to Dave, what's the best way to get reach of you?
Just email me. It's just dave.aitel@cordyceps.systems. Super simple.
All right, perfect. Otherwise, Dave is a very active member of the Discord server chat community at Neo4j. So if you are a member of that, you know where we are. If you don't, I'll put the link into the video description as well. All right, with that, thank you very much, everybody. And yeah, see you soon. Bye.